Thank you, Mr. Chairman, and it's a pleasure to talk with you. My compliments to the organizers of the symposium. I think this is an excellent discussion. I'm proud to be part of it. You've heard a lot about fuels, and our question is, what do you do with them after you have them? So the next two papers you hear, this one's going to be primarily about conversion, and the next paper that Tom will give will be about storage. So heterogeneous functional materials, or HeteroFoaMs, as we call them, are the materials we use to do that, both convert and store fuel. And the fuels that we've been discussing are the context that I'm going to use to start this discussion. So we'll go immediately to that discussion. First of all, we've been using fuels for something like 400 years in some manner or other, and of course technology, as we know very well, has been driving what fuels we use and how we use them. And as the technologies change, the fuels change. But what's amazing is that we're still depending on that fossil juice that we got from the dinosaurs to do most of what we're doing. And that's changing, and this conference is good evidence of that. If we can have renewable, sustainable sources, then we have a brighter future in many respects. This is, of course, a chart that looks a lot like the one Sam Baldwin used, and it's pretty similar in most respects. These feed lines are changing, if you can see them, the ones that come from natural gas especially. And what's happening on the right-hand side is also changing to some extent as far as proportions. But we're using about 100 quads. A quad is a train of coal that goes from, one quad, that goes from New Mexico to the top of Alaska. That's a pretty large chunk of stuff. And we're using 100 of those. There are about 460 or so of these are used in the world per year. So we have a lot of fuel. It's already different. It's going to get more different and diverse as we go forward. So that's our problem that we're trying to deal with. Who's going to use that? Population grows, fuel grows, but where is it growing? Everybody would get this right? The stable part of these curves about what we need in the way of power are the dark spots that we're familiar with. The part that's growing most rapidly is the rest of the world, and there's a lot of those parts. This, I'm not sure you can read, but it's what about affordability? How much are we paying for fuel? And all you really need to do is to see that these curves are going down, and that's how much we're paying over a period of years, and this is 1950. Some people, at least in the audience, were around in 1950, right? So this is not that long a period of time. We hear about externalities now, and even if we account for emissions and so on, the cost of fuel is still going down compared to what it was. So if we have a terribly expensive solution, we're probably not going to affect it on our society. What's this one? It says, well, what fuels are we using? And each one of these lines is a fuel. And you can see that on the left there are a few, and on the right there are a bunch. And if you could extend this past 2035, there'd be a whole lot more. Yes, fuels are diverse, and they're going to be a lot more diverse. Well, you've seen this chart before. We're lucky in the sense that the demand is close to one possible source, and that's one that's dominated a good deal of our discussion. So that's part of the happy news. And we're certainly going to take advantage of that, I think, in the SEC group of universities. But there isn't just one solution. And you've seen various numbers. I actually had to X this out and put some question marks in because since the first day of this conference, we've heard numbers as low as 17 and as high as 80 put into that. If we turned everything we're able to grow into fuel, what would the percentage be? And how many answers do we get? So this thing seems to be changing on its own, but nevertheless, there's not just one example of a fuel that we need. And what's wrong with this diagram? Any farmers in the audience? It's the wrong end. Thank you for that. This is a German diagram. I guess I don't know if I should say that or not, but anyway. So we need lots of diversity. We need to deal with different fuels. Well, we're trying to do that, and this group knows this story pretty well. And we have a fairly diverse set of fuels to work with, but even within these divisions, especially for the bio part, there is still a lot of different kinds to deal with, but still we have energy coming from all of these types, a fair amount of it, of course, from these other sources as well. And it's renewable. and we need to deal with it. So converting and storing are what we're about, and that's largely what this center is about. We're going to have energy conversion and storage challenges for a very diverse fuel stream. And these are the greatest challenges we have to deal with, in my opinion, as far as technology and science are concerned. So we have to learn how to convert it to power when we need it and where we need it. And both of those are difficult. We also have to prevent choking ourselves. So this business is a sort of punchline for us because we believe in fire without smoke. And I'm going to talk about fire without smoke in a couple of moments. We can convert these fuels to power without smoke. One way to do this, of course, is a high-temperature fuel cell. Now, these things are as common as a large building in New York City. It's about 4 of them by now, are run by these things, or the police station in Central Park of New York City, run by these, and just hundreds of buildings around the world. High temperature solid oxide, molten carbonate, phos acid, actually more of these than anything else. But the advantage of high temperature, of course, is that we can change the nature of the fuels we're working with in a very direct way. What we are doing, of course, is finally deploying in our society. You can buy now a low temperature fuel cell in an automobile, and we can use hydrogen to get around without polluting the atmosphere as well. But we have a lot of other fuels, and we'd like to be able to use them. The flexibility of a solid oxide fuel cell, it has no precious metal catalyst, for example, so I don't have to go looking for those. Fuel flexibility, which I've been picking on, and a number of thermodynamic advantages as well as far as incorporating this into a system. Disadvantages, of course, are costs and a variety of other application difficulties that we're still trying to deal with. Fuel flexibility, well, we can deal with all of these sources, including peanut butter, beer. I mean, we've demonstrated all kinds of things, burned 15 or so fuels in a single fuel cell in our laboratory without any difficulty at all. So yes, the diversity here is there. We can go from any 2 points on this chart to a third point with a solid oxide fuel cell. So it's really a converter. We can split things, for example, if we have a fuel into primary elements, if we have other power around. And of course, we can combine fuels to make heat or electricity and so on. So the advantage of this technology is that it's a universal converter. Probably parts of this chart you can read. Maybe you can see up here that this is efficiency, and this is the solid oxide fuel cell part, and it is extremely diverse across a very large, it's the most scalable technology we have available to us. And this is sort of how it works. We have 2 elements that would like to be together. If we isolate them in a sufficient way, we can extract the power that they're willing to give up in order to be joined together in a compound. Most of everyone in this audience, I think, is familiar with this. The General Motors would like us to believe you can drink the results of that. I'm not completely sure that's correct, but nevertheless, the last chart over here has to do with how much pollution is provided. And we could get now about 72% efficiency if you join this with a combined cycle turbine, for example, which would be a pretty nice increase, especially since the amount of emissions that you can see out of that would be very, very small. All right, so this is what we'd like to do. This is the temperatures we'd like to run out. What are the materials we use to do that? Well, they're the materials that have holes in them. They're heterogeneous, and they are HeteroFoaMs in the sense that they transport elements back and forth. And you'll hear about the next lecture how this happens in a different way, but we sometimes have gases or fluids that have to go through these holes. There have to be different kinds of these because it works a bit like a battery in the sense that you have a cathode and anode, and you can't have conduction through this thing or it shorts itself out and the game is over. So yes, we have to have ionic and electronic conductors. Nowadays, we have ionic conductors that are nearly as good as the electronic ones. A real revolution, an honest revolution in this field. So how do we make these things and what do they look like? This is just outrageous fun, I have to tell you, for a person who's been in materials for all their life. We can now, believe it or not, design and actually make the specifics of these details that you're looking at down to the atomic level. Couldn't do that even 5 years ago. So if we can make it look like something, then what should it look like? What should the size of the holes be? What should the interfaces between the elements be? How big should they be? How small should they be? If I get small enough, I don't have an actual compound. I lose character after about 9 atoms. So smaller isn't necessarily better in all cases. So how do I put this stuff together, and what do I use to do it? And that's what our center is about, as I mentioned before, with a bunch of people trying to figure that out. I'm going to skip this slide. It simply says, I put it up here because of the magic picture. But anyway, we are indeed interested in liquid fuels. I want to make that point. This technology works with liquid fuels. We use JP8, for example, from the aircraft industry that makes the Army happy. But we could also use liquid fuels that are made from the biosources that we've been discussing. We do operate at temperatures of a few hundred centigrade, so we do have to worry about material changes. Well, we have a center. There are 40 of these things throughout the United States. The Energy Frontier Research Center is funded by the Department of Energy. This one's located there. And the people that are involved in this, these are some of the universities, Princeton and so on, at Oak Ridge National Lab. And here are the people that do all the work that I'm privileged to stand up here and talk about. The folks from Georgia Tech, involved in surface behavior for the most part. We have folks that worry about where the atomic orbitals are and what they are doing to store and convert energy. And this is an incredibly interesting field. You heard Dave Dixon talk about this a little bit with molecular orbitals. This is mostly density functional theory at the Princeton crowd. But nevertheless, we have a group that does indeed design catalysts from the ground up, where the atoms are, what they actually do. Folks that put it together with additive manufacturing schemes, and a variety of people that are interested, for example, in surface kinetics and how does something actually happen at the surface of these materials to make them work. Integrated modeling people, this is University of Connecticut. Some of the people who can do just about everything, but Anil Varkar is the best thermodynamicist I have ever seen in my life and is able to tell us when we actually have our potentials in the right spot and might get a reaction we expect. Okay, so a couple of examples of what we do, just to point out why these kinds of materials are important, these so-called HeteroFoaMs. If you want to have fun, you can go to HeteroFoaM.com and see some folks make fools of themselves in videos. But nevertheless, the thing we did was take the analysis that we're doing down to the atomic and to the meso level. If we have something that has holes in it, it has constituents that we've been able to resolve here in this case, and the sides of this thing are a few nanometers. So these are pretty small pieces of stuff. How do we get down there and find out what they're actually doing? And as you heard in the previous lecture, the arrangement of matters a lot at this scale. The electrons only go where they'd like to go, or the ions, and we have to move both of those guys. And in some cases, a bit of mass as well to get the fuel there. So we took the analysis down to the local level. That's the first step. It sounds simple, right? I just go get some COMSOL analysis, and I set this stuff on. Well, it doesn't quite that simple. What are the boundary conditions? How does this work? And if it really does have mass, momentum, energy, and charge in a balance equation, what does that equation look like, and are there constitutive relations between the coefficients? And the answer is yes. These are coupled, strongly coupled, by temperature, who is surprised, but by other things as well. Coupled problems, multiphysics, local level, first step. Then we'd like to design these guys. Okay, I have some white stuff and some black stuff. Should I stack them up together, or maybe I intermingle them? You heard a bit of this before from one of our other speakers. When do they actually conduct the best? And if I have a chemical reaction going on here, and then I have transport of charge, how do I get both those things to happen, and how do I put these parts together? And there is actually a sequence that we have established in our research group, this center group, for doing this. If I have a starting point with some materials and I can design them a certain way, how do I finally get to the philosophy that will give me the best results? A lot of surprises, and they tend to happen at surfaces. We think we have this figured out in the bulk, Then we get a surface and we get a big surprise about what happens. So arrangement. Then what can we do with this? Well, I've talked about fuel cells a little bit, or tried to. This is actually a capacitor. These are fascinating. You can increase the capacitance storage capability of charge in a material by 6 orders of magnitude with things you buy in a Home Depot store. 6 orders of magnitude. Well, I don't know, but that's sort of interesting stuff, because I can go in with my grandson and I mix this stuff up, and this stuff has, you know, very small capability to store charge, and that one is 6 orders of magnitude better. Well, sorry about that, let's try again. There are reasons why we'd like to make a better capacitor, right? We have capacitors over here that store charge quickly. We put them in cars when you brake so that you can grab it fast. We have batteries over here that store it pretty well and for a long time, but they don't last very long from the standpoint of cycles, for example. And they have other problems, as you've been reading about in Boeing literature recently, the newspapers. Fuel cells that have a lot of advantages, as I've talked about before, but their power density is not as great. We'd like to be up here on this right-hand side of this chart, where the energy density and power density, how quick I can do something is power, right? How long I can do it is energy density. I'd like to have both of those things. Well, capacitors probably could do that. We're not up here. We're right about there with the capacitors we're making presently. How did we do that? The guys this is led by Mei-Lin Liu at Georgia Tech, and of course help from the rest of the team, by storing charge in an arrangement of things at the nano level. Intentional, by the way. One more application of this that's sort of fun. Where do I get all this so-called precious metal and the other stuff that we'd like to use in the motors that we put in electric cars, for example, the permanent magnets and so on? And for another problem related to this, I have a lot of nuclear waste to deal with, and by the way, in this region of SEC region we do. How do I extract that stuff so that I can handle it in some way and store it more easily, or maybe even recycle it? And the answer is solid membranes. For example, if I have a nuclear waste and it's an oxide and I pass that through at a sufficient temperature, if I have something that conducts the oxygen out, I can pull the oxygen out and I have the good stuff left. That's being done as we speak, and it's being done at our university. This extraction of ions is an ion conduction process, but of course, when ions go one way, electrons have to go the other. So this is a mixed conductor. And it's made intentionally by mixing materials. They're heterogeneous, just like the conduction process. This is a refinement that was created by Savannah River National Lab and ourselves working together in the center, the HeteroFoaM Center. And it's going to enable, these are the number of elements we use as a function of years. And the right-hand side is where we are presently. And you can't quite see it, but this is essentially a turn of the century, and this is where we are currently. We're using about 80 elements at the present time. And there aren't a lot more than that, right? So where do they come from? Unfortunately, in places in our country very often, but we have those elements. We're just adverse to trying to go after them, and we don't have good processes that are economical to do that. But this solid oxide membrane, or solid membrane in general, is a way to solve this problem. The Germans are going after this in full glory as we speak, and so is the United States. One more point, and you're going to hear more about flow batteries as an alternative solution to this, and you've heard a good deal about plating out lithium as a metal. If you get lithium metal in a lithium ion battery, you have a big problem, and Boeing can attest to that. That can happen, of course, if you try to recharge it too quickly, which appears, just from a non-expert person, to be what happened with the Boeing situation. But still, think about this fundamental thing. I have a battery, I want to have it be stable, but I want to have it give me power as quick as possible, and I want to be able to get power back into it as quick as possible, which is really an instability, right? I want to have a really big instability, but I want this thing to be stable when I have it. And that's tough to do. And John Goodenough, as you know, has won every national prize we have to give in this country for inventing this process in the first place, but it's inherently unstable if you do it extremely well. So there are limitations. How do you design? And this is now a design. It's a geometric design, a morphological design, a chemical design, and a mechanical design in order to make that battery correct. Well, are there other places in society? We didn't talk about photovoltaics, but of course we could. You've heard a good deal about that from people who know much more about it than I do. Batteries, you're going to hear about flow batteries in a minute. And here's the synaptic cleft. Well, it turns out that this idea of heterogeneous materials that have flow of charge across a heterojunction is a very old one. We borrowed it from biology, right? And the guys that come back with traumatic stress syndrome very often have this difficulty in their spine. Something disturbs this distribution of charge between these two synapses, and they don't function correctly. So there are applications of this science and this technology in other areas. And we're hoping to go there. Biomass, this is, again, a difficult slide to make any sense out of, but it does tell you that the Savannah River National Lab people, as well as Clemson University in our state, South Carolina, are indeed working very hard to pursue the HeteroFoaM business with biomass. And finally, I wanted to talk about, just for 30 seconds, about sequestration. Some of us are not so sure that you can stick it underground. And I just want to be sure that everyone knows there's another way to do this, at least one other way that makes a lot of sense, and that is close the loop. If we can indeed somehow or other split CO2 and make things like liquid fuel and hydrogen out of it, and you can do that if you have power over here from these sources or any other source to do electrolysis, then this liquid fuel, of course, can be cycled through anything, let's hope a fuel cell, and used again when these things are released. We do not have to bury CO2. We can indeed make liquid fuel out of it, and the devices that I've been talking about are used for that purpose as well. All right, I'm finished. We had support from the Department of Energy and about 4 other organizations, but this is the biggest player. Thank you very much for your attention.
Questions from the audience? Well, can I have one question? You mentioned about to replace the catalyst in the fuel cells. So what do you think in the future, especially from your work, what would be the materials or heteromaterials that plays an important role to replace platinum or precious metals in the fuel cell?
Yeah, we're at such high temperatures that on the anode side where the fuel is, something like nickel is more than willing to split a petroleum atom or a hydrocarbon atom without any additional material. Now, we can actually even do it with a ceramic now, but we're not talking about replacing catalysis. We're just replacing the extra stuff we put in there to do the catalytic work. And at high temperature, there's so much driving energy that we can do that with some pretty ordinary stuff.
Okay.
So I can send some papers if you want to hear more about the details of that.
Sure. Any other questions from the audience? Yes.
So what would be the energetics if you look at for the CO2 to the liquid fuels? Do you think going uphill that we're really ever going to create energy, or is that just sort of a losing game from the beginning? I know it's possible to do it, but do we really want to?
As you may know, we've been trying to do this since 1939. This is a process invented in the Germans in 1939. And the economics of it change every day. The energetics are still being worked out in detail depending upon the process, just like the stuff you guys are doing. Personally, okay, I'm outrageous, but I think closing that loop should be a bigger priority than trying to find a rock cap that's sufficiently good to keep that stuff from getting out when I bury 36 million tons of it in a year for the United States. I can't see that. I think we'd better learn to do science rather than to dig a hole.
Okay, let's thank him again.